Okay, so welcome back. Hopefully you've given this one a try. So what I've done is I've graphed negative 3 times 0.7 to the exponent of x plus 2 on Desmo, so let's see what we can answer. So first up, before I even look at the graph, I can tell you the parent function is just going to be 0.7 to the x. So your base is 0.7, and without transformation, it's just going to be an exponent of x. So your mapping rule then, so again, first look at what's happening to the exponent, that's your x. It's x plus 2, which means it's shifted left 2 units, which means it's going to be x minus 2 in the mapping rule. Okay, as for the y value, well, there's no vertical shift here, otherwise you'd see something out here. So all we have right now is this negative 3 that's multiplied by the y value that gives you a vertical stretch and a reflection. So our mapping rule is going to be x minus 2 and then negative 3y. Okay, for our horizontal asymptote, we should be able to see here that there's no vertical shift here, so the asymptote will be at y equals 0, and I'll let you confirm that by seeing the graph right here. Okay, the asymptote is going to be at y equals 0. And then we can take it a little step further and see what else we can get. So the domain will be all real numbers, as it will be for any exponential function I'll run into, unless there's some sort of real-life restriction. The range in this case, if you look at the graph, is going to be anything below the asymptote, because we've been reflected here. So it's going to be any y value that is less than 0, strictly less than 0. Is there an x-intercept on this? You might think there is by taking a quick look at the graph, but remember the asymptote is there at y equals 0, so we can't actually cross that spot right there. We can get infinitely close to it but never actually touch it. So there is no y-intercept, or sorry, no x-intercept here. For the y-intercept, you can see it on the graph if you look for it. You can see it's at about negative 1.47. But remember, we can always calculate it because it means that x is equal to 0. Okay, so if we were to take our function right down here and replace x with 0, we should be able to calculate it. So we get negative 3 times 0.7 to the 0 plus 2. So 0.7 all squared is 0.49, which times negative 3 gives you that negative 1.47. Okay, and is it increasing or decreasing? Okay, we can see from the graph it is increasing. And again, another way you could think about that is if we were just take a look at our parent function here, we have y equals 0.7 to the x. Okay, that's increasing, but this reflection right here brings it across the x-axis, so now we are going to be increasing instead of decreasing. Okay, so with all that in mind, that's, again, gives you a pretty good idea of how to get all the main features from the equation from the graph. We'll take a look a bit more later about how to get a sketch. But for now, let's move on and do something else. So what I want you to do, just take a look at a function here, y equals 2 to the x, and you can fill in the table of values for this relatively quickly. So when x is 0, y will be 2 to the exponent 0, which is 1. When x is 1, 2 to the exponent 1 is 2, and so on and so forth. So I'll do that part for you. I'll fill in that table of values. What I'd like you to do now is do the first, second, and third differences and see if you can recognize any patterns. What you may remember is from grade 9 that the first differences of a linear function were all the same. In grade 10, the second differences for a quadratic equation were all the same. And let's see if there's any pattern here with an exponential function such as y equals 2 to the x. So give that a try first. Fill in those differences and see if you can see any patterns. Okay, so take a second here and check your differences. You may notice here that at no point are you going to get any differences that are the same. Okay, it's not going to be like something linear or quadratic. We're eventually going to run into something where all differences are identical, so you can make a determination. What you are going to notice here is that if you look at all the differences, there is a common theme that you're seeing, and that's what you're seeing. Instead of a common difference, you're seeing a common ratio between the differences. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and so on and so forth. So the differences are always doubling as you move from one to the next. So what you're seeing here is a constant difference, and is it a coincidence here that it's doubling when the base here is 2? It is not. So that when these differences here, you're going to have a common ratio that's going to be equal to the base of your power here. So if this is y equals 0.5 to the x, these differences would be halving. If it was y equals 3 to the x, they'd be tripling as you move down. So that would be a kind of pattern that you see with differences in an exponential function. Okay, so with that in mind, hopefully now you should be able to finish completing this worksheet. So anything you haven't been able to do so far, you should be able to do the rest now. Once you finish that, I'd like you to make sure you do numbers 1 to 3 on page 423, which doesn't take very, very long. Okay, so I'm going to quickly stop here. So if you haven't done that yet, do that work now. When you're finished it, just come right back to this video because I'm going to continue on through the rest of the lesson. Okay, so just as a recap before we go any further, again, just taking a look at parent functions, not any without looking at any transformations, just looking at the parent functions, we're just looking at f of x equals a to the x. Just to remind yourself, what makes it increase or decrease? It all depends strictly on the base. So the base is larger than 1, we have something representing growth. The base is between 0 and 1, we have something that represents decay, it is decreasing. Okay, so let me just quickly show you on Desmos. Okay, so what you can see here are examples of two different functions, one where the base is larger than 1, and you'll see it's increasing, the black one right here, and one where the base is smaller than 1, between 0 and 1, and you'll see this one's decreasing. Okay, and again, for an exponential function, the base has to be larger than 0. You can't have any negative bases. Okay, so again, that's just a bit of a recap there. Some other things that you can remind yourself of is that you can always find the horizontal asymptote by looking at that vertical shift. So here it's written as y equals cube. It can be whatever letter. All that matters is that whatever the vertical translation or vertical shift is gives you that horizontal asymptote. So y equals whatever the vertical shift is. Okay, so that's all stuff we saw in the first part of this lesson. Okay, so if you want to look at whether an exponential function increases or decreases, well, it's going to depend on two things. Number one, you're going to look at the parent function. If the parent function increases or decreases, you can tell that just by looking at the base and give you a starting point right there. But then you also have to keep in mind that it could be reflected as well. So if it's been reflected, there's going to be a change of whether it's increasing or decreasing. So it makes a note here. It says how many. It's also based on how many times the function is reflected across an axis. So if it's been reflected once, it's the opposite of the parent function. If it's been reflected twice, it's the same as the parent function. Now this two reflections thing is mainly just put in here as a note. For those of you taking 3U next semester, when we deal with what we call reflections across the y-axis, you're going to be dealing with situations where you have potentially something being reflected twice. In 3M, we're only going to be mainly dealing with the one reflection case, so where it's been reflected across the x-axis. So if there has been a reflection, then it will be reflected across the x-axis and change from increasing to decreasing or vice versa. Going back to Desmos, just so we can see that, for example, here's y equals 1.3 to the x. When we put a reflection out in front, let's say we're multiplying this by -2, all of a sudden, adding that negative out in front has changed it from increasing to decreasing. Okay, and you'll see increasing, decreasing. Okay, for this 0.2 to the x, this is now decreasing because if you look at the parent function, the base is less than 1. Again, if you add a reflection to it, all of a sudden you see it's now increasing from left to right. Okay, so you get that general shape and whether it's increasing or decreasing just by looking at that parent function and whether or not it's been reflected. Okay, and some other things to summarize here, just to what we talked about using differences. With linear functions, think back to grade 9, you had constant first differences. Quadratics, you had constant second differences. You would wind up with constant third differences if you had something called a cubic, something that had an exponent of 3. Okay, you're going to be seeing a lot more of those in 3U next semester, those of you going on to take that. But in exponential functions, none of your differences are constant. What you, again, have is a common ratio. And that common ratio is going to be equal to the base of the exponent, base of the power, sorry. Okay, so again, all that's just summarizing what we looked at briefly in the first part of this lesson. Now let's try and take one example that's going to put everything together. So I'm going to have you make your own sketch here once we generate an equation. So first off, we're given f of x equals 6 to the exponent x. So right away from there we have our parent function. So there's a lot you can tell from that parent function. The base is larger than 1, so it's going to be increasing. Okay, but again, we'll see what happens once we have a transformed version. Because the first thing it asks us to do is to develop an equation for y equals -3 f bracket x plus 4 minus 7. Okay, now in here, it comes up often over and over again. Don't get scared off by the function notation. All I'm asking you to do is apply this to the original function right here. So remember, what does f of x plus 4 means? Well, it means take f of x, wherever you see an x, you're replacing with x plus 4. So the f of x plus 4 bit right here is simply going to be 6 to the exponent of x plus 4. Okay, so now I'm going to multiply that by -3. So negative 3 times 6 to the exponent x plus 4. Then, of course, I have the minus 7 right here. So this is going to be my equation I'm going to be working with. Okay, so it's a transformed version of the parent function 6 to the exponent x. So how do I get the mapping rule? So again, for the mapping rule, look at what's happening to x. It's x plus 4, which means it's going to be x minus 4 in the mapping rule. Okay, and as for what's happening to y, well, I have a negative 3 out here, which gives me my vertical stretch and my reflection in the x-axis, and it's shifted down 7. Okay, so right away you could also see from there that this will be my horizontal asymptote. So I'll use HA for short. That might come in handy later making my sketch. My horizontal asymptote is going to be at y equals negative 7. Okay, so I should already have in my mind an idea of a sketch for this. So I haven't asked for it yet, but picture this being a Cartesian plane. I already know my asymptote is going to be at y equals negative 7. So somewhere down there is going to be an asymptote. Now in terms of my general shape of the graph, okay, my parent function, y equals 6 to the x, will be increasing from left to right, so it's that kind of general shape. Okay, but it's been reflected. So it's been reflected on the across the x-axis. So now, what does it look like when it's reflected? Well, I'll have the mirror image of it like this. Okay, so this will be the general shape of my function after it's been reflected. Well, is it going to be above or below the asymptote? Well, if it's above the asymptote, you'll see what's going to happen. I'd be drawing this like this, and all of a sudden my graph would cross the asymptote, which can't happen. Okay, so it's not going to be that. It's going to have to be below the asymptote. So my sketch is going to look something like this. Okay, there's not a lot of detail on this, but I do know my asymptote is at y equals negative 7. And this is the general shape of my graph. So this is something I can have in the back of my mind without doing much work. Once I have my equation, I know I have a reflection, I know where my asymptote is, I can get this general sketch right there and just add more details as I find them out. So once I have this picture, find the domain and range is actually pretty straightforward. I know the domain is going to be x is an element of the real numbers. Okay, there's no restrictions on x. But as for my range from the picture, I can see that I can only have y values that are smaller than negative 7. So my range will be y is less than negative 7. Okay, and I can skip d and even look at e and say, hey, my function is clearly going to be decreasing from my sketch. If I didn't have that sketch in my mind, I could think, okay, my parent function is increasing because the base is larger than 1, and I have one reflection here, so it's going from increasing to decreasing. And again, that matches my picture right here, decreasing from left to right. Okay, so as for the y-intercept, I should be able to calculate that by, again, letting x be equal to 0. Okay, I don't have Desmos to help me out here. So I'm going to have y equals negative 3, 6th exponent of 0 plus 4, which is just 4, minus 7. Okay, I just need to run this through my calculator. So when all said and done, it's a y-intercept of negative 3,895. Okay, and I should be able to add that on my graph as well. Okay, you can clearly tell this graph is not to scale, but it is just a sketch. So I have my general shape and I have all my key points labeled, so there's nothing wrong with that. Okay, and last but not least, describe my transformations. Okay, well I can get those directly from the mapping rule. So from the mapping rule I can see I have a vertical stretch, which I'll use VS for short. There's a vertical stretch of factor 3. Okay, that negative means I have a reflection in the x-axis. Okay, I'll see if that x minus 4 means I go left 4. And then again, of course, down 7 as well. Okay, and last but not least, it asks for a sketch. Well, I've really already done my sketch. I put everything together up here. In terms of what I'm looking for a sketch, all I want is the general shape right, my asymptote drawn in, and a variable my key points like my y-intercept being clearly labeled. That's all I'm going to ask for a graph. Okay, so you can see by looking at the equation, okay, that's what it generally looks like. Again, your shape might look a little bit different, but the same general shape is going to be there. You're going to have the right asymptote, and again, even though mine's not drawn to scale up here, I can still have my y-intercept drawn in at negative 3,895. Okay, as long as you have all that information, you'll have everything you need to get full marks. Okay, so please make sure you practice by doing these examples right here, and all that's left in this unit is to look at some word problems. Okay, that's it, that's all.